So doing this using a limit in the summation means we're going to do a limit as n approaches infinity of the sum from k equals 1 to n of 3 x sub k squared minus x sub k minus 1 times delta x. So f of x sub k times delta x. And then we have to figure out what delta x is, and we have to figure out what x sub k is. And delta x, as we talked about the other day, is always b minus a over n. So that's 2 minus 1 over n, or 1 over n. And x sub k is always a plus k delta x, or in this case, 1 plus k over n. Everybody good with that so far? Yeah. All right, cool. So then we'll just replace the x sub k's with 1 plus k over n and the delta x with 1 over n, and proceed to evaluate from there. The first part changes, and then we've got 3 times 1 plus k over n squared minus the quantity 1 plus k over n minus 1 times 1 over n. Everybody still good there? Just replacing the x sub k's, making sure that that x sub k gets put into parentheses once you replace it.
Yeah.
All right. Then we'll do all the distributing. So this becomes a limit as n approaches infinity of the sum from k equals 1 to n. And so 1 plus k over n starts out with a 1 when I distribute that out, when I square it. And so that 3 is going to get multiplied by a 1, so that'll be 3. And then I'm going to have a 2k over n in there, which will become a 6k over n when I multiply it by the 3. And a k squared over n squared, which will become a 3k squared over n squared. We're going to have a minus 1. We're going to have a minus k over n. And we're going to have a minus 1. And then that's all going to be multiplied by 1 over n. Everyone good there?
Yeah.
And then we'll combine any like terms. So we got 3 minus a 1 is a 1. And then the 1 times the 1 over n will just be 1 over n. We have a 6k over n minus a k over n is a 5k over n. So that becomes plus 5k over n squared. And then we have a 3k squared over n squared, which will become a 3k squared over n cubed. And then now we'll go in, and anytime we have a constant, which is this, the 1 over n, we're summing together n of those. So that just becomes 1 over n times n when we do the summation part. So we have the limit as n approaches infinity of n over n. And then the k becomes n times n plus 1 over 2. And we'll keep the 5 over n squared. And then the k squared becomes n times n plus 1 times 2n plus 1 over 6. And we will keep the 3 over n cubed. Everybody good so far doing the summation part?
Oh yeah. Where do we prove that k squared equals n plus 1 times 2n plus 1 again?
We did that on Monday. We didn't do the proof. I just told you guys that that's what it was equal to. But
Okay.
said you need to memorize that. But yeah, it is. We did that on Monday. So now the n over n part is 1. This is 5n squared over 2n squared as the highest degree part. So that's 5 halves. And then this is 6n cubed over 6n cubed, so plus another 1. So it looks like that should come out to be 9 halves.
Where did the 6k over n come from?
6k over n came from distributing out 1 plus k over n squared. So if you distribute out the 1 plus k over n squared, that's 1 plus 2k over n plus k squared over n squared. And then distributing the 3 through it gave us the 3 and the 6k and then the 3k squared.
Okay, thank you.
Everybody good with that one? That's probably as complicated as they'll get. I'm not going to give you guys anything that's worse than a quadratic to do with the limit and the summation, because they get really complicated otherwise and require you to know a bunch of stuff that a bunch of different summations rather than just ones of constants here, or with k's or k squared. They require you to know a bunch of other ones that I wouldn't expect you to know and that you would learn until you took a second semester of calculus. Any other questions on that? Or any of the rectangular or trapezoidal approximations, or any of the other integrals using Newton's notation? That's what we're going to start off with tomorrow. I said yesterday. Tomorrow we'll start off with that. Have our quiz. All right, I'm going to assume from your silence that everybody is good. Is that a reasonable assumption?
Yeah.
All right. If you have questions, send me a remind message tonight on it, or email, I guess, but remind usually gets you a quicker answer because that pops up on my phone immediately. All right, let's start talking about some new stuff. So we're going to get into, rather than just an area underneath the curve, we're going to really get into what an integral is all about and start thinking about some easier ways to find integrals. And in order to do that, we have to talk about this thing called the fundamental theorem of calculus. And the fundamental theorem of calculus has two different parts to it. And we're going to talk about both parts right off the bat. And then we're going to sort of combine the two of them together to sort of piece it all together as a whole and say this is what an integral really is and how we can find one more easily. So the first part of the fundamental theorem of calculus, which is sometimes called the antiderivative part, just tells us that the derivative and the integral are inverse operations of each other. And so that if I were to take the integral of a function and then take the derivative of that new function that I got, I would end up with the same function that I started with. Okay. So if I were to say, what is the integral of the derivative of x? You would say it's x. Or if I said, what's the integral of the derivative of sine squared of x cubed? You'd say it's sine squared of x cubed. Right? Derivatives and integrals, or sometimes called antiderivatives, this is another word for an integral, an antiderivative, are just opposite operations of each other. Very important. Now, there are some sort of little caveats to that we're going to work through, but in general, that's the case. Derivatives and integrals, or derivatives and antiderivatives, are just opposite operations of each other. So you've probably noted that every time we've done an integral, like all these integrals up here that we did, like this one had an upper limit and a lower limit on it. True? And this had an upper limit and a lower limit. This had an upper limit and a lower limit on it. And this did, and this did, and this did. They all did, right? All of them had an upper limit and a lower limit. Well, when we put these upper limits and lower limits on them that are just numbers, both constants or numbers, what it's doing is it's telling us an area between the x-axis and that curve. It's giving us a number out, right? Everything we got was a number. We got a number for this. When we did these ones in class, we got numbers for them, right? But that's not all that antiderivatives or integrals are about. Sometimes they are about finding a function that represents the area underneath the curve for any certain range of values. So ignore everything that's written up here for now, except for this. Suppose I have some function f. Okay, and there's my function f. Okay. This thing right here says the integral from a to x of f of t dt. And that tells me that if I want to find the area underneath this curve f of t from a, some constant, to any other x value, right? If I want to find this area, there is some function that represents that area from some number to any other number x. So for example, if I said, instead of a here, if I said 1, then there is some function that represents the area from 1 to any other x value, right? So if f of t, let's say f of t was, I don't know, that's not a very, let's just pretend f of t was, we'll just say it's like t cubed minus t or something like that. I know that's not the right function, but suppose it was that. Well, there is some other function that represents the area from 1 to any other x value underneath this curve. That function happens to be t to the 4th over 4 minus t squared over 2 minus, what is that minus 2, no, just that, t to the 4th minus 4 minus t squared over 2. And so if I were to use this for any value, suppose I plugged in 3 to this, that would tell me the area from 1 to 3 of this function. Or if I plugged in 7 to this, it would tell me the area between 1 and 7. Or if I were to plug in 1,000,000, it would tell me the area between 1 and 1,000,000 underneath this function. So an integral is not always just a number. Sometimes it is represented by a function. Okay. Is that okay with you guys or no?
So that equation at the bottom of the graph would be the integral function?
Yes. Yeah, I guess I could leave that all up there.
Okay.
I don't know what happened to the rest of it. The rest of it's not showing. But whatever equation I wrote down there, which was 2 to the 4th over 4 minus t squared over 2. Yeah, that is called the integral function of it. Yes. And that's developed by combining together the first and the second parts of the fundamental theorem of calculus, which we're going to get into in a second. So there's a way to say, all right, from some value to some other value, there is this function that represents the area. And that's a very important piece to all of this. And I know it seems a little weird at the moment because everything we've done so far was just finding a specific area between two numbers. But that's okay. In addition to that, we can also have an integral, and suppose I just put in, let's just say I put this. This doesn't have an upper or a lower limit at all. True? You all agree that that doesn't have an upper or lower limit at all? The integral of x cubed dx?
Yep.
Yeah. Well, this, when I find the value of this, it is a function. There's not a numerical value to it. And that function represents the area underneath this curve on any interval that I choose. So suppose I chose an interval 1 to 2, I could use the function that I get out by performing this operation. I could evaluate that on the interval from 1 to 2 and find the area. Or I could use it to evaluate the area from 1 to 3. Or I could use it to evaluate the area from -7 to 300. As long as I can find the generic function that represents this area under this curve. by taking an antiderivative or by taking an integral. And the way we do that is by doing the opposite of taking a derivative. So we're going to basically be doing all of the derivative rules in reverse with our integrals. Does that sort of make sense?
And if we were to, let's say we do like -7 to -1, would our numerical value be from the distance between the curve and the x-axis still?
Yeah. Yes, it would.
And it would be positive or negative?
Well, it depends. So if the function's above the x-axis, it'll be positive. If the function's below the x-axis, it'll be negative. And if the function crosses through the x-axis, the pieces that are below will come out as negative, and the pieces that are above will come out as positive, and they'll sort of cancel each other out. But for now, we're not going to worry about the distinction between area and the integral itself. We're just going to worry about the value of the integral until we get into our unit about area.
And do all integrals have a dx to them?
If the function inside of here is in terms of x, yes, they have a dx to it. This one's in terms of t, so it has a dt. You know, you could have an integral of y cubed, it'd have a dy attached to it. If you had an integral of theta squared, it'll have a d theta attached to it. Yeah. They'll all have something in there that's attached to it. The d something, whatever the variable happens to be. And remember that d theta or dy or dx or dt or whatever it happens to be is just the tiny little width of each of the rectangles that we draw, the infinite number of rectangles that we draw to sum together using that integral. Does that make sense?
Yeah.
Okay. Cool. I know it's a lot at the moment, but that's okay. So basically, from part one of this fundamental theorem of calculus, and we're going to come back to this page in a second, the important thing to understand is that the derivative of the integral of a function is just that function. Okay? And we're going to talk about why this went from a t to an x in a second, but that requires the second part of the fundamental theorem of calculus. But the important piece is the derivative of the integral of something. This effectively cancels itself out, and you just end up with the original function. Everybody okay with that conceptually?
Yeah.
Okay, cool. So we're going to add a second piece to this and then sort of throw it all together to where it hopefully makes some sense. The second part of the fundamental theorem of calculus says, if I can find the function that is the antiderivative of this thing, f of x, and I have what we call a definite integral with an upper and a lower limit, the way that you find it, the way that you find the numeric value of this is by taking the integral function or the antiderivative. So it's like capital F is a function, just like we were talking about before, where I came up with that like t to the 4th over 4 minus t squared over 2 thing. That's like a capital F. That's the antiderivative function. And then you evaluate it at B and at A and find the difference. So that's exactly what a definite integral is going to tell us to do. And so we're going to find some tricks for doing this that don't require us to use that limit and that summation. So before, right, when we were doing this, we did all this hard work and we did the limit. We were like, limit is n approaches infinity, and the sum from k equals 1 to n, 1 minus 6x sub k squared times delta x. And we didn't get a little function in there, right? We just came up with this limit and this summation, did all this work. Well, from now on, what we're going to do is instead of doing all that work, we're going to find a function that is the opposite operation of derivative. Hold on one second. Sorry about that. Okay, so what we're going to do is we're going to find this function, capital F, that represents the antiderivative, represents the area underneath the curve, and then we're going to evaluate it at B and evaluate it at A, find the difference, and that's going to come out to be the same numerical number that we got from doing all of this work. Does that sort of make sense?
Yeah.
All right. Cool. Let us see if we can piece all of these ideas together then. So I'm going to go back here and I'm going to erase, except that I don't have my eraser showing up. Cool. It'd be cool if my eraser was here. All right, I don't have an eraser, so I'll do it on this page instead. Okay. We're going to say that the integral from a to x of some function f of t dt is equal to capital F of x. Okay, that the integral of little f, basically the function that represents, and I'm going to write this out in words, that represents the integral of little f is capital F. Okay. And so according to the fundamental theorem of calculus, part 2, if capital F is the integral function, then the second part of the fundamental theorem of calculus says that if I were to take the integral from a to x, I should find the function that is the integral of little f, which is capital F. I should evaluate it at x, and I should evaluate it at a, and I should find the difference between the two of them. Right? That's exactly what this said right here. And if I had from a to b, this little f, if capital F is the antiderivative, we find the difference between them. So that's what I've done here, except instead of having a to b, I have a to x. Everybody okay with that? That's just second part of the fundamental theorem. Good or no?
Good.
With capital F being the integral function of little f. So now what I want to do is I want to take the derivative of this integral of little f of t dt, which would be the same as taking the derivative of this, wouldn't it? Right, if this is equal to this, then the derivative of this ought to be equal to the derivative of this. True?
Sure.
All right, so using the first part of the fundamental theorem of calculus, if the derivative and the antiderivative are opposite operations of each other, and capital F is the antiderivative or the integral of little f, what should the derivative of capital F of x be? So remember that the derivative and integral are opposite operations. Okay. So the integral of little f is capital F. So what should the derivative of capital F be?
Little f.
It should be little f. So the derivative of capital F of x ought to be little f of x. And what about the derivative of capital F of a? What does a always represent? A is just a number, right? That's sort of what I drew in this picture back here. A was, I eventually replaced it with 1, but A was just some number where we were looking for the area from, right? So A is a number. And if capital F is a function, right? What do you get if you evaluate a function at a number? Generically, what do you get?
The number.
You just get a number, right? If I take some function and evaluate it at a number, I get a number. And what happens if I take the derivative of a number?
0.
You get 0. And so the derivative of the integral from any constant to x of any function is just that function in terms of this variable x that we had up in the upper limit. That's the proof of how derivatives and antiderivatives are opposite operations of each other. And that idea is fundamental to the entire process of doing calculus. So, any questions on that? I know that's a lot of stuff, a lot of conceptual stuff, but any questions on that? The whole point of all of this is this thing at the very end here, that the derivative of the integral from a constant to x of any function is just that function that you started with. And that incorporates both the first and the second parts of the fundamental theorem of calculus. Okay. I'm going to hope that that silence is because it all made sense and not because you're all completely lost. So, generally, on the AP test, they will give you a couple of questions that ask you to deal with the fundamental theorem of calculus. So they will ask you something like, what is the derivative of the integral from this constant to x of some function? And so based on what we've just talked about, what is the derivative of the integral from a constant to x of some function?
The function.
It's just the function in terms of this new variable up there. It's just equal to cosine x. That's all the fundamental theorem of calculus is saying. Good or no?
Wait, so what is the negative pi? What does that mean?
It's just
Or how
some
does that-
constant. It's just a constant. So what it's saying is, so here's what we're going to do. I'm going to write this all out. We're going to say there is some function, and we're going to call it capital F, such that capital F is equal to the integral from negative pi to x. Well, let's just say is equal to the integral of cosine t dt. So capital F is a function, and I'm gonna write this. What I'm gonna say, or capital F represents the area under the cosine curve. Okay. So we're just gonna make up some function, and we could probably figure out what that function is, but we're not going to yet. There is some function, we're calling it capital F, so that capital F is the integral of cosine of t dt, or F represents the area underneath the cosine curve. So we're just saying there's some function that's true. There's some function that makes that happen. And so the second part of the fundamental theorem of calculus says that we take that capital F function and we evaluate it at this upper limit. And then we subtract that capital F function and evaluate it at that lower limit. Okay? And so then what we want is the derivative of that. So we've got the derivative of this integral using the second part of fundamental theorem of calculus of the function capital F that represents the integral of cosine. And so that negative pi is really just a constant in there. It says we're looking for the area between negative pi and any other x value on the cosine function. So let me really quickly, and hopefully I can get Desmos to work. Oh, good, it did. Here's our cosine function. And here's negative pi, right? There is some function, we're calling it capital F, that represents the area between cosine x and the x-axis from negative pi to any other x value that we choose. We might choose 1, right? Or we might choose pi over 2, or we might choose a negative 5 pi over 2. We could choose any x value we want. But there is some algebraic function that represents the area between the x-axis and the curve cosine x from negative pi to any x value. And that's what we're calling capital F. Does that make sense what the negative pi is there for? It's just the starting point for where we're finding the area underneath this curve. Okay, cool. Let's see, this is the one we were working on here. So now we've done this whole piece. That's this, capital F of x minus capital F of negative pi. And now we still need to take the derivative. So when we take the derivative of capital F of x, since we know from the first part of the fundamental theorem of calculus that the derivative of the antiderivative, or the derivative of the integral, is just the original function, the derivative of capital F of x ends up being cosine x. And then the derivative of this, right, capital F of a number is just a number, and its derivative is 0. And that's how we end up getting cosine x. That make sense? Or no?
Yes, thank you.
So all of this is the first and second part of the fundamental theorem of calculus, and it's what's going on behind the scenes as we look for the value of all of this to be cosine x. And we should be able to just make this jump and say, well, this is the derivative of an integral from a constant to x of some function, so it's just that function in terms of x. But this is what's really going on. This is what we're really doing to get cosine x as the answer. Any questions on that? I know it's a conceptual week, and it's hard for me to gauge whether you're understanding what we're talking about very well because I can't see you and whatnot. But if you're having issues, please let me know. All right. So what about this one? The derivative of the integral from 0 to x of this function, 1 over 1 plus t squared dt. What should this be?
One over 1 plus x squared.
It should just be 1 over 1 plus x squared, right? That is coming from the same idea. We could come up with some make-believe function that we'll call capital F, or we could call it whatever we want. Capital F is the antiderivative of this. So we'd get capital F of x minus capital F of 0. And then we'd take the derivative of that, and the derivative of capital F for this problem would be 1 over 1 plus x squared. And the derivative of capital F of 0 is just a constant. So the derivative of the constant is just 0. Good or no?
Do you have to do anything with the domain if one of your bound numbers is outside the domain?
I will, for this class, you will never get any domain values, or you never get any upper or lower limits that are not defined on your function. And in fact, the entire interval between, oftentimes most of the time we'll have 2 numbers here, rather than, we'll either have no number, we'll have nothing here attached to the interval, no upper or lower limit, or we'll have 2 numbers. And the entire interval from 0 to whatever this is, let's say 10, will always be defined on that entire interval for this class. When you go to higher calculus classes, sometimes you'll have to deal with discontinuities in there and stuff, but not for this class.
Okay, got it. Thank you.
So for those of you that are having the joy of coming back for BC next year or taking Calc 2 in college, you'll get to deal with that. Don't worry, I promise it's not that hard. Speaking of that, how many of you are planning on taking BC next year? This is probably not the best time to ask after all this conceptual crap.
Is it required?
Is it required? Yes, I'm going to say yes, it's required. No, it's not required. I was curious if any of you are planning to. I'm sure some of you are planning to. So. How many of you are juniors? I don't know why I'm asking that because I'm not going to get like an actual answer. 17 of you? Okay, cool. We're going to pretend that's how many of you are juniors. So those 17 of you could come back and take BC. I promise it's more fun in person. All right. Let's see if we can do this with something that gets a little bit more complicated now. Just what you wanted, right? It to be a little bit more complicated. So we're going to find the derivative of this function y if y is equal to the integral from 1 to x squared of cosine t dt. So it's very similar to what we were just doing. We're still finding the derivative of an integral from a constant to a function instead of a variable this time, not just a variable, but a function of some other function. So let's call capital F the antiderivative of cosine t. And using the second part of the fundamental theorem of calculus, what is y equal? What is this integral equal to? If capital F is the antiderivative of cosine t.
F of x squared minus f of 1.
Capital F of x squared minus capital F of 1. And we want to find the derivative of y with respect to x. So we want to find the derivative with respect to x of capital F of x squared minus capital F of 1. So how do we find the derivative of capital F of x squared?
The derivative and the capital F cancel out.
The derivative and the capital F cancel out. So that's going to give us back to this original function, right? Cosine x squared. But this is a function within another function. And when you take the derivative of a function within another function, what rule do you have to use?
Chain rule.
Chain rule. So rather than just taking the derivative of capital F to get cosine and evaluating it at x squared, we have to multiply that by the derivative of
X squared.
x squared, which is 2x. And we're going to say chain rule, derivative of x squared. And what about here? What about when I take the derivative of capital F of 1? Well, capital F of 1 is just a number. And so that goes away. It just becomes 0. And our answer is 2x cosine of x squared. Good or no?
Why didn't you change the cosine to negative sign?
Because we didn't have cosine up here. We had the function that was the antiderivative of cosine, which is capital F.
Oh, okay.
And so if we were, well, yeah, I don't want to get fully into that right now, but does that make sense? This is not the cosine function. This is the new function that when I take its derivative, I get cosine.
Yeah, I got you.
So, I mean, and we can think about that. What function is the function that when I take its derivative, I get cosine? What function do I take the derivative of to get cosine?
Sine.
Sine, right? F is actually, this is the sine function. So really what we could have written here was, we could have said, this is sine of x squared, because that's the function that when I take its derivative, I get cosine, minus sine of 1. And how do we find the derivative of sine of x squared? Well, it's cosine of x squared times the derivative of x squared, 2x cosine x squared. And what's the sine of 1? It's just some number, so its derivative is 0, and it goes away. So that's intuitively how we're going to find these functions that are the antiderivatives, is because we know all the derivatives. Well, we don't know all the derivatives, but we know most of the derivatives. So if we just do those things in reverse, those should be our integrals or our antiderivatives. Does that make sense to everyone?
Yeah.
All right, cool. So let's look at this one. We want to find the derivative of the integral from 0 to x squared of e to the t squared. So now this one, e to the t squared, you probably don't know what function you can take the derivative of to get e to the t squared. So we're just going to call capital F is an antiderivative of e to the t squared. And so this becomes the derivative of capital F of x squared minus capital F of 0, just like we did up here. And the derivative of capital F now for this problem, what's the derivative of capital F? If that's the antiderivative of this, the derivative of F should be this thing evaluated at
X squared.
x squared, so e to the x squared squared, and then times the derivative of the x squared, 2x, and then minus 0, or 2x e to the x to the 4th. Good or no?
Good.
All right. Let's do another one. This one's a little bit different because this one, what's going on here?
We have multiple terms.
Right. Well, there's there's a 3t sine t.
Yeah.
Yeah, and also the constant is no longer in the upper limit. Sorry, in the lower limit, it's in the upper limit, right? So if we call capital F an antiderivative of 3t sine t, what does this end up being when we take the antiderivative of 3t sine t from x to 5? We do capital F of which thing first? The upper limit or the lower limit?
The upper limit.
The upper limit. So we'll have capital F of 5 minus capital F of x. And that's what we're trying to find the derivative of. And what's the derivative of capital F of 5?
0.
0. So we just end up with now a negative this function in terms of x, negative 3x sine x. Good or no?
So the fact that there's two like separate functions doesn't affect it.
Doesn't affect it at all, right? Not one bit, because we can still say, all right, there's some function that is the antiderivative of this. We may not know how to find it. In fact, you definitely don't know how to find it and won't learn how to find the function that represents the antiderivative of this in this class. But we know that there is some function that does represent it. And that when I take its derivative, it comes back to this original function. Okay. Now, we'll note that if this had been the other way around, 5 to x instead of x to 5, what would our answer have been instead?
The same but positive.
The same but positive, right? There's a rule, and we would have gotten to it in a minute, but we're going to go skip to it right now. There's a rule. Where is it? There it is. There's a rule right here, and we're going to come back to this page, so you don't need to bother to write it down right now. That says if you want to flip the limits of integration, the upper limit and the lower limit, you can do that. You can flip the upper and the lower limits of integration and just put a negative sign outside that integral. And so if we think about it, we had x to 5 and gave us a negative. If we'd had 5 to x, like we just said, it would have given us the positive. And that makes perfect sense because of this rule. You can flip the limits and get a negative. So if I'd flipped the limits, and in fact, let's do this over here. I could have said this is the same as the opposite of the integral from 5 to x of 3t sine t dt. And then when I did this whole process, I would have ended up with 3x sine x with a negative in front of it. So this is just sort of also in addition to what we already did. We could have thought about it this way if we had known that rule in advance, which we didn't, but now we will. Everybody okay with that?
Yeah.
We had to use the chain rule before, right? But we don't have to use the product rule here. Is that accurate?
We do not need to use the product rule because we're not taking the derivative of a function within another function. So the reason to use the chain rule is because here we were taking the derivative of a function with a function composed inside of it, right? But here we're not doing that, and we're also not taking the derivative of a product of two functions. This is just a function evaluated at x. So we're taking its derivative, and we already know what the derivative of capital F is. It's 3t sine t. Because we
Thank you.
capital F as such.
Okay, that makes sense.
Cool. Yeah, good. Keep the questions coming if you guys have questions, because I know this is like algebraically, the work is pretty there's not a lot of work, and our answer is not a lot different from where we started, but conceptually there's a lot going on. So I want to make sure we understand it. We're going to do one more of these. And then we're going to talk about some rules and a couple other little cool things, and then we're going to be done. And I thought we were going to be done like 20 minutes early, but it doesn't look like we will be. So since we now have 15 minutes left. So we're going to do one more of these. And notice this one, there is no what?
Constant.
There is no constant in our upper or lower limit. Both the lower limit and the upper limit are functions. But we can still proceed in the same manner. We can say, let's call capital F an antiderivative of 1 over, 2 plus e to the t. So if capital F is the function that represents an antiderivative of this, then the integral from 2x to x squared of this ought to be capital F of the upper limit minus capital F of the lower limit. And we want to find the derivative of that. And so for each piece of this now, we have a function with a function composed inside of it, right? A function with x squared composed inside of it and a function with 2x composed inside of it. So both of these are a function within a function. And so each of these derivatives requires us to use which rule?
Chain.
The chain rule. So the first one ought to be, what's the derivative of x squared?
2x.
2x. And then we should be multiplying that by the derivative of capital F evaluated at x squared. So the derivative of capital F is this function. And so we'll just plug in x squared into this function. So over 2 plus e to the x squared. And then here, it should be minus, what's the derivative of 2x?
2.
2. And it should be times 1 over 2 plus e to the, and this time we're plugging in 2x. And that's our answer. Good or no?
Should we always state the variable that we're calling the antiderivative?
You should, if you are going to write it out that way. Yeah, you should.
Okay.
Yeah. And one, I might have done it once. I might have mislabeled something slightly. If I did, I'm going to go back and fix it. You should always say that it is an antiderivative of it, not the antiderivative of it. I think one of these times I think I wrote the, yeah. So I should write is an antiderivative of this, because every function, this is going to sound weird, but it'll make sense tomorrow a lot more. Every function, like cosine of t, there are an infinite number of antiderivatives to this. There are an infinite number of antiderivatives to 3t sine t. There are an infinite number of antiderivatives to 1 over 2 plus e to the t. As soon as we slap limits on it, that's when there's one specific value for it. But before I slap these limits on it, if I'm just talking about an antiderivative of this function, there are an infinite number of different antiderivatives for this. And we'll talk about why that is in a little bit. Well, not in a little bit, but we'll talk about it tomorrow. So make sure that you say it is an antiderivative, not the antiderivative. All right, everybody good so far?
Yeah.
Okay. Now, I know that was a lot and it took almost the entire period and probably a lot of things rattling in your brain about it. And I'm going to probably frustrate you slightly now by saying they're going to ask you a question or two about this on the AP test using these fundamental theorem of calculus things. And then you'll probably never, ever see any of that again in your life, and you won't ever see any of it again in this class, other than when I make you practice this to be prepared for the AP test. Because this is not what we will be doing the majority of the time with antiderivatives. We're going to be actively actually finding what the area underneath the curve is. And we're going to be putting numbers into it and evaluating these things. And we're not going to have these annoying little derivatives of antiderivatives with functions in the upper and the lower limit. We're either, 99.9% of the time, we're either going to have no limits or we're going to have numbers for both of the limits. But this shows up on the AP test, and that's why we've got to talk about these conceptual stuff behind it. So, cool. We talked about one rule for antiderivatives, one rule for our integrals. There are a few other rules for integrals that we need to know and be able to apply before we can really, really, really tomorrow get into what we're really doing with integrals. And so those rules are what's up here, the rest of these. One, if I have a constant times a function inside the integral, I can take that constant and pull it outside the integral. And pull a constant out, just like we've done with limits, just like we did with derivatives, just like we've done literally with everything else we've done this year with our summations, with everything. If there's a constant inside of it, you can pull it out. So where did it go? This 3t sine t, there was a 3 in front of that, right? I could have taken that 3 out of the integral, done all the work, and then multiplied my answer by 3, and we would have got the exact same thing. Good?
Good.
Yeah.
All right. Next important rule is if I have two functions being added together within an integral or subtracted, I can separate those into two different integrals with the same limit. So if I have an integral from a to b of f plus g, that's the same as the integral from a to b of f plus the integral from a to b of g. Next, and also very important, if I want to find the integral from a to a, or from 2 to 2, or 7 to 7 of some function, it will always 100% of the time be equal to 0. And why is that? Here's some function. Here's A. What does an integral represent?
The area between
The area between those two values, right? So what's the area between here and here? Well, there's literally no width between there. So can there be an area if there is 0 width?
No.
No. So the area from somewhere to itself is just 0. It doesn't matter what the function is. There will never be an area if we have no interval. And then lastly, this has a lot to do with our area stuff. If I have an integral from A to B and an integral from B to C, so the area from A to B plus the area from B to C ought to be the area from A to C. Does that make sense? If you think about it in terms of area underneath the curve.
Yeah.
Yeah, and likewise, if I knew what the area from A to C was, and I knew what the area from B to C was, I could subtract A to C minus B to C, and that would give me A to B. So I can rearrange this as needed to find any of those area values. Good? All right, things are going to get much easier now. We're going to do this last page and then we're going to be done for the day. We might still be done 2 or 3 minutes early. I'm going to give you the value of the integrals of a few different functions. We're going to apply those rules and then we're going to be done for the day. So we know that the integral from 1 to 2 of f of x is -4. The integral from 1 to 5 of f of x is 6. And the integral from 1 to 5 of g of x is 8. What's the integral from 2 to 2 of g of x?
It would be 0, right?
Should be 0, right? Didn't we just have a rule, right? The integral from a to a, from 2 to 2 of any function is 0. So the integral from 2 to 2 of any function is 0. What about this one for 5 to 1? Which of those rules do I need to apply?
The one with the opposite bounds.
Well, we want to say exactly. This is the opposite of the integral from 1 to 5 of g of x dx, which should be the opposite of
8.
8. Easy enough. See, we went from the really, really complicated stuff to the much easier stuff now. Good or no?
Good.
All right, what about this one? What rule can I apply to this one?
The constant one.
Yeah, we can take that constant out and say this is 3 times the integral from 1 to 2 of f of x dx. And that becomes 3 times, what's the integral from 1 to 2 of f of x?
-4.
-4, so this is -12. And what about this one? The integral from 2 to 5. Which of those rules can we use?
Subtract 1 to 2 from 1 to 5.
So 1 to 5 of f minus 1 to 2 of f, which ought to be 6 minus -4, which ought to be 10. And what about this one? This ought to be the integral of 1 to 5 of x, sorry, f of x, minus the integral from 1 to 5 of g of x. And since we have both of those, what do we end up with? Should be 6 minus 8 or -2. Good or no?
Good.
All right. That's spectacular. Anybody have any questions on anything we've done today? before I ramble for 2 or 3 more minutes and then end class. That was enough for somebody to leave. I guess they had no questions and didn't want to listen to me ramble. All right.